So we have said that centripetal force is any force that causes something to move in a circle. Okay, so let's make that a little bit more specific. A centripetal force is any force that contributes to centripetal acceleration. So when something is moving in a circle, it is accelerating centripetally. And so then we can use Newton's second law here. F net equals ma. That's Newton's second law. And if we're talking about circular motion in particular, this acceleration is actually centripetal acceleration. So we can just put that AC in there. And this net force is any set of forces that are causing that centripetal acceleration. So we would call that FC, or centripetal force. So the centripetal force is equal to the mass times the centripetal acceleration. Okay, that's just the second law, and we've just made it specific to circular motion. Now we have an equation for centripetal acceleration, right? And so this becomes centripetal force is equal to mass times v squared over r, speed squared divided by radius, mv squared over r. And that is our version of Newton's second law specifically applied to circular motion. Now let's try example 1. A piece of string can sustain a force of 20 newtons before breaking. Can it be used to safely swing a 1 kilogram rock around in a circle with a radius of 1.5 meters if the rock is traveling at 5 meters per second? It's a weird situation. Only in physics do you try and swing rocks around in a circle at the end of a rope. Or if you're my son, he would definitely do that. So we know the maximum force, this 20 newtons. We know the maximum force the string can sustain, but we don't actually know what force the rope needs to exert in order to swing a 1 kilogram rock in a 1.5 meter circle at 5 meters per second. Okay, so we're not going to use that 20 newtons in the equation. We're going to figure out what is the centripetal force and then compare that centripetal force to the 20 newtons. We know will break the rope. Okay, so we're going to go like this. Centripetal force is equal to mass times v squared over r. And let's fill in some numbers here. So the mass is 1 kilogram. The speed is 5 meters per second. And the radius is 1.5 meters. Now, all of those units are exactly the units that we want in this equation, so we don't need to change any of that stuff. It's really just this straightforward. And so we're going to do that calculation. And when you calculate it out, you get 16.67 newtons. And so the answer is no, the rope will not break. So if we were putting a direction on this thing, we would say toward the center. But since the point of the question is whether the rope is going to break or not, I'm not too fussy about you shoving a direction in there. So this is no, the rope will not break. A car with a mass of 1,250 kilograms is traveling on a concrete surface with a coefficient of friction of 0.75. What is the maximum speed the car can have if the radius of the car's path is 125 meters? We are trying to figure out maximum speed. Okay, so let's make a list here of all of the things that it gives us and what we're looking for so that we can organize our thoughts a little bit and form a process for solving this. Okay, it gives us mass, 1,250 kilograms. It gives us the coefficient of friction, that's new. And the radius of the circle. Now, often when you do this, when you make this list, you can see an obvious formula that you're going to use to find the missing piece. In this case, these things just do not work together very well, but we should ask ourselves, what do these three things give us that we can then use to figure out the velocity or the speed? So I can see this m and this r over here. They could be part of that centripetal force equals mv squared over r situation. The problem is then that I don't have centripetal force, right? I have no way of calculating what the centripetal force is. But that's really all that I have to work with, right? So I'm going to write it down, and then we can think a little bit. So centripetal force is mv squared over r. And I know that I'm going to split centripetal force into its pieces. But now when we think about this, what are all the forces that are causing a car to move in a circle? So here's the curve that the car is taking. If there was no friction, a car would just continue moving in a straight line, right? You'd turn the wheels, but it wouldn't turn unless there was friction. So it's not like there's a rope pulling you in a circle. It's not like your engine is pulling you in a circle even. It's the contact with the road and the tires. That's pulling you in a circle. So it's only friction. And so when I think about what are all the forces contributing to this car moving in a circle, it's really just friction. So my centripetal force is just friction in this case. Okay, remember that centripetal force is not its own type of force. It's just F net for things moving in a circle. So if the situation is a circular motion situation, you're just doing F net equals ma. It's just that F net is now centripetal force, and ma is now mv squared over r. Okay, so a lot of people get a little bit confused with trying to figure out what's the centripetal force from the question, when that's not it at all. Centripetal force is just net force. It's just the sum of the forces involved in a circular motion question. So we can just split F net into what all those forces are, and sometimes it's just going to be one of them. That's this case. So the force of friction is mv squared over r, but it still doesn't tell me the force of friction in the question. Luckily, we have a formula for that. So it's the coefficient times the normal force. And it doesn't tell us the normal force either, but this is a level surface. This isn't a banked curve. This is just a level curve. And so that tells us that the force of gravity and the normal force should be equal to each other, right? The force of gravity is pulling everything down, and since this car is not accelerating through the road or being tossed in the air, then it's got to have a balance between the normal force and the force of gravity. And so this becomes mu mg. Okay, mg is the force of gravity, equals mv squared over r. Okay, now I see that I don't actually need mass from this question, right? Look, there's mass on both sides. There's mass there, and so I can cancel it out of both sides. So interestingly enough, the mass of a vehicle does not actually matter to how quickly it can, or to how fast it can be going when it goes around a curve. That doesn't make any difference. So when engineers are designing a roadway and figuring out what is the curvature of the road we should use, they don't need to ask themselves what's the average or what's the maximum weight of a car. They don't need to take that into account at all. Interesting tidbit. So we can actually cancel out the mass, though in this case it does tell us what the mass is. So we could also just throw that number in there and do that calculation as well. I'm going to just simplify things a little bit and not include it. So I'm trying to calculate V. So I'm going to divide by R and square root this thing. So I end up with the square root of the coefficient times 9.8 divided by R. Okay, so now I'm going to put in my 0.75 for the coefficient. I'm going to put in my 9.8 for gravity and put in my 125 meters for the radius and then square root it. And what I get is 30.3 meters per second. We're going to do one more centripetal force example, and this is the advanced one. It's kind of how we go. A plane is flying in a vertical circle with a radius of 400 meters. The pilot, has a mass of 70 kilograms and is flying the plane with a speed of 65 meters per second. Calculate the normal force on the pilot in both of the following situations: the lowest point and the highest point in the circle. Okay, so before we actually do any calculations, let's take a little picture. Look at what's going on here. Here's the chair. Here's the pilot. Ooh, perfect. Okay, so now let's think about the forces acting on this pilot. This is what I want. Okay, so when this pilot is flying in a circle, we're not thinking about what are the forces acting on the plane. We're thinking about what are the forces acting on the pilot. Okay, so the pilot is going to experience the force of gravity pulling down. Everything does all the time. And the pilot is going to also experience a normal force from the seat pushing up on him. Right? If the force of gravity was pulling him down and the seat was not holding him up, he would just fall to the ground. Okay? And those two things, the combination of those two things, is contributing to the circular motion. Okay? And so the centripetal force, in this case, at the lowest point in a circle, this plane is going to start doing this. Right? It's going to swing upward, and so the centripetal force is going to be toward the center of the circle. So the total centripetal force is this way. Okay? But that's not a separate thing. We're saying that the normal force and the force of gravity, when you add them together, they're going to give you this centripetal force vector. Okay? So let's do this calculation. Centripetal force is equal to mv squared over r. Okay, so we've just set up our F net formula for moving in a circle. Now we've got to split centripetal force into the forces that are involved in the circular motion. And so the forces that are involved are the force of gravity and the normal force. Okay, so it's not like we're not putting centripetal force, normal force, and gravity in the formula all at once, because the centripetal force is made up of the force of gravity and the normal force. Okay, so don't put all three of those things in there. The centripetal force is not its own thing, it's a combination of the two. Sorry for beating that to death, but it happens all the time. So I'm splitting Fc into its pieces, and I'm going to go with the normal force being positive and gravity being negative. Okay, and I've made that decision because my total, my centripetal force, I know is going to be upward at the bottom of the circle. Okay, and so this is what I've done. So my normal force is upward, my force of gravity is going to be downward, and that gives me mv squared over r. And so now I want to account for all the numbers that I'm given in the question. I'm told the radius is 400 meters. I'm told the mass of the pilot is 70 kilograms, and the speed is 65 meters per second. So my normal force is going to be the force that's holding the pilot up. I want to solve for that thing. So often on a level surface we say that the force of gravity and the normal force are the same. And that's true except when the system is accelerating, right? So if you're standing in an elevator and the elevator starts to suddenly rise upward, to accelerate upward, you feel like you are being squished down, right? So the normal force is actually exerting more force on you when the whole elevator is accelerating upward. Okay, so the normal force isn't always equal to the force of gravity on a level surface, only when the whole system is not accelerating. Okay, and in this case it is. So we're not going to just put in mg for the normal force, and if we did that, you can see what would happen right away. Mg minus mg is 0. The whole thing is just done. So we're not going to do that. We're going to leave it. So the normal force is equal to mv squared over r plus the force of gravity. Just doing the algebra step right there. So we've got 70 kilograms times 65 meters per second squared divided by 400 meters. And onto that we are going to add mg, or 70 kilograms, times 9.8 meters per second squared. Now I'm not going to cancel out the 70 and the 70 because that is not found in every term, right? The 70 kilograms is not found in my normal force. In other circumstances it would be, but not in this one. So when I calculate this out, I get a normal force of 1,425 newtons upward. I get a positive 1,425. Okay, and if we think about this for a second more, this is the force of gravity here. Excuse me. And the force of gravity is 686 newtons. Okay, so under normal circumstances, if this plane was just flying horizontally, not in a circle, then the normal force that the pilot would be experiencing would be 686 newtons. But because the pilot is accelerating in a circle, then the normal force is going to be a little bit greater. You're going to feel like you're being pressed into the seat, right? And so the normal force is going to be greater than the normal force of gravity would be. So the second part is the very same, except the position has changed. So if I can remember how to draw this. Here's the seat. Here's the pilot. Legs, arms. There you go. And so now if we put in the directions of all the forces, you've got the force of gravity pulling straight down. You've got the normal force also pulling straight down. I didn't purposely draw them different directions or the same direction. I don't know how close they are to one another, and so don't read anything into the size of the arrows. And the centripetal force, again, not a different force, but it's what these two add up to. The centripetal force is also down. Okay, so the combination of the normal force and the force of gravity are also going to be down. That doesn't really help me with much in the calculation side of things. It just gives me a clue about what I should name positive and negative. Though in this case that hopefully was clear already. If everything is happening downward, I'm going to call that my positive direction, and negative is going to be my upward direction. You don't have to do it that way. You don't have to avoid using negatives like I tend to, but I just find that I'm going to make fewer mistakes if I tend toward using as much positive as I can. So we're going to do the exact same thing as before. Centripetal force is mv squared over r. Split centripetal force into its pieces, which are the normal force and the force of gravity. This time I'm making them both positive since they're both down. Again, I am not including centripetal force here because that is not its own force. That's the combination of the normal force and the force of gravity. And so now I'm trying to solve for the normal force again. So in this case, it's going to be the normal force is equal to mv squared over r minus the force of gravity. Okay, that's really the only thing that has changed in this whole thing. And so the normal force is 70 kilograms times 65 meters per second. Square that. Divided by 400 meters minus 70 kilograms times 9.8 meters per second squared. Okay, it's the exact same situation. It's just that I'm subtracting the force of gravity instead of adding it. And so the normal force that I get now is 53.4 newtons down.